So we've talked a bit about some of the key terms and phrases and ideas within algebra. We're going to dig a little bit deeper even in this video. Right. So we've talked about how algebra is the study of relations and operations, and how an operation is a procedure that produces a new, in parentheses, output value from one or more input values. And the operations that we're used to, the main operations that you first learn in elementary school, are all binary operations. Right? So we talk about 3 plus 5, or 3 times 5. And so we have two inputs. The inputs here are called factors. This is our product. The inputs here, we've definitely talked about this, are called terms. And the output here is called the sum. And subtraction also has two inputs, division. So bringing in fractions here. Has two inputs and then an output. The output here is called the quotient. The output here is called the difference. You see already from this example, to deal with a negative number, I'm really thinking of this as the operation addition with that extra piece put in here. And we'll do the same thing with division when we start talking about fractions soon. We're really going to think about this as a multiplication, where that division part is being applied to that second input value. But so long as it's written with the division symbol, the order here very much matters. The order here very much matters because you need to see that that dash is applying to that 5, not to the 3. That the division is applying to the 5, not to the 15. So we'll get to this later. Right now we just need these words. What we have to remember for just now is that because division can be thought of as multiplication, all of the ways signs work within multiplication also work for division. So just very quickly, if I have negative 15 divided by 5, I've got a single negative here, that would be negative 3. If I have negative 15 divided by negative 5, I have the opposite of a negative, that's a positive, just as if I were multiplying, right? Because it is really multiplication. It just doesn't quite look that way. So dividing sign numbers works exactly the same way as multiplying sign numbers. Now, the reason why I'm putting these examples here with our definitions is because not all operations have exactly two inputs. We can actually think about this as an operation. What do we do with 2 to make it negative? I'm putting that dash in front of it. You could think of that as an operation all by itself instead of thinking of it as multiplying by negative 1, the opposite operation. If you remember, if you took trig in high school, right, the trig functions are operations that only have one input. They're called unary operations. You're taking the sine of a particular angle or the tangent of a particular input value. But all of these, one or more input values, all of these have two input values. They're binary operations. And we have to remember that when we look at the commutative and the associative property. The commutative property states that the order of the inputs for a single operation is immaterial, or is not relevant. Now, there are different ways you can phrase it, but the classic way of writing it is to say, come on, A plus B equals B plus A. 3 plus 5 is the same as 5 plus 3. Right? If I've got 3 dots here and I add 5 to it, that's the same as if I started with those 5 and I add 3 to it. Right? If we're just counting, that's very clear. If I'm drawing my arrows, a 3-inch long arrow followed by a 5-inch long arrow, that's the same as a 5-inch long arrow followed by a 3-inch long arrow, right? That sum is still going to be 5, or it's still going to be 8. Right? And it's the same with multiplication. We saw that with our index cards. Whether I call the length 5 and the length 3 and the width 5, or I call the length 5 and the width 3, the area of that index card is still going to be 15. If I add up a bunch of 3's, or if I add up 5 3's or add up 3 5's, either way, I get 15. Right? That's the commutative property. To commute means to reverse the order. Right? So if you think of, in our everyday speech, you might commute to work. You're going from your house to work, and then from work back to your house. Same 2 locations. It's an office building. I don't know. Same 2 locations, just going from one to the other and back again, right? 3 plus 5, 5 plus 3, same thing. 3 times 5, 5 times 3, same thing, right? So both addition and multiplication have this property. It's a property of the operation. The associative property is a little bit different. It also has to do with order. Both addition and multiplication for real numbers have the associative property, just like the commutative property. But it's slightly different. The associative property, just put it here and put a return in there, says that when the same operation is done multiple times, the individual instances, sorry, the order of instances, the order of the individual instances of that operation is not relevant. That's a bit of a mouthful. All right, so go ahead and make sure you write that down. For the associative property of whichever operation has this property, it's saying when the same operation is done multiple times together, the order of the individual instances of that operation is not relevant. So let's take a look at that. For a binary operation, if I have something like, switch back to my pen here. If I have something like 3 plus 5 plus 2, I have 2 different additions here. I can take these two as my inputs and add 3 plus 5 is 8. And then that sum is now the input for the second addition. I'm adding these two. That is the input for this operation, the first of the two inputs for this operation. 8 plus 2 is 10. Or for this first addition here, instead of taking 3 and 5 as the inputs, I could take 3 as one input, and then all of this, that's a plus sign, as a second input. 5 plus 2 is 7. 3 plus 7 is also 10. I'm going to get the same result here, whether I associate my 5 with the 2 or associate the 5 with the 3. When I have these multiple instances of addition, I get to choose which terms are associated with which other terms, whether I do this addition first or this addition first, right? 5's choosing whom it associates with, right? Your associate is someone you hang out with, your law associate, your business partner, your buddies, your friends, right? 5's associating with 3 or 5's associating with 2, doesn't matter, same result. The same is true for multiplication. If I take 3 times 5 times 2, I can associate the 5 with the 3, do this multiplication first, and then use that product as the input for the next multiplication. 15 times 2 is 30. Or I can associate the 5 with the 2, perform this multiplication first. 5 times 2 is 10. 3 times 10 is 30. Okay. We've already used that property, but now we're stating it officially. And we can see for multiplication, that should be very clear if we think about our definition based on area. If I take an index card that's 3 by 5, I can twist that around any way I want. It's still going to be a 3 by 5 index card. It doesn't matter which is the length or which is the width. Well, if I make that now a box that's 2 inches deep, I'll draw that fairly nicely. Well, I can spin around that box however I like. It's still 3 by 5 by 2. I can get 15 and double that to get 30, or I can get 5 by 2. That's my lid here. This is 5, this is 5, this is 5. So 5 by 2, and take 1, 2, 3 stacked piles of 10. 10 times 3 is 30. Or I can do the 3 by 2 to get one side here, right? If this is 3, this is 3, it's a rectangle. 6 times 5, that's 30. I can associate these factors in whatever arrangement I want. I'm still going to get the same product in the end, right? But I'm only doing one multiplication at a time. Unless you're a quantum computer, you can't really do more than one multiplication at a time. Now, this doesn't work for subtraction or division for a very straightforward reason. Subtraction isn't just putting 3 and 5 together as inputs. It's saying this is applying to one in the way it's not applying to the other. So if I'm changing the order of which subtraction I do, if this is changing the direction of the 5, it's not changing the direction of the 2. This is not the same as this, right? each reverse is only applying to the term immediately following. So as soon as I change this -5 into plus -5, and change this -2 into plus -2, now it's addition. Now I am free to either do 3 minus 5 is -2, or -5 plus -2. The 3 plus is still there. -5 and -2, both negative, both moving to the left. 3 plus -7, -4. Once we rewrite our subtraction as addition, we can use the associative property just fine. X is the associative property of addition. In this instance, 3 is just 3. I'm getting the opposite of 5 minus 2. Well, 5 minus 2 is 3. The opposite of 3, -3, 3 plus -3, that's giving me 0, a very different answer. Even if I write this as 5 plus -2, I'm still getting 3 here, and then applying this negative to all of that, that doesn't work out. What's going on here? I'm applying the negative to the 5, as I should. The 5 is negative. But I'm also applying that negative to this 2 that already had a negative in front of it. I'm doubling up this to become a positive 2. I'm thinking of this as 3 with the -5, and then the opposite of negative giving me a positive 2 instead of 3 and a -5 and a -2. I've changed the direction of this last term by putting these parentheses in here. So if no parentheses are there, don't create them. Don't try to use the associative property when it's not appropriate. You always want to think, even if you don't actually write this step, you want to think about this as an addition problem. Recognize that that dash only applies to the 5. And then this dash applies to the 2, making it going left, making it go left, not go right.